Hello everyone, welcome to this lecture. So, in this lecture we will have a recap of the BGW MPC protocol for passive corruptions. So, for the full details of the BGW MPC protocol for passive corruptions, you are referred to the Secure Computation Part 1 course. We will see the exact reference at the end of the lecture. So, the plan for the lecture is as follows. We will try to understand the principle behind the BGW MPC protocol, namely the shared circuit evaluation. So, what is the setting of the BGW MPC protocol? So, BGW MPC protocol was invented by Benor, Goldwasser and Wigderson. So, that is why the name BGW. It was published in 1988, and what is the setting considered in this MPC protocol? So, recall that the problem of secure computation or MPC can be studied in various dimensions depending upon how you are abstracting your underlying function to be securely computed, what is the type of underlying network, what is the corruption capacity of the adversary, whether the adversary is computationally bounded or unbounded, whether the adversary is corrupting in a passive fashion or malicious fashion, and whether the adversary is static or adaptive. So, the exact dimensions studied captured in the BGW protocol is as follows. So, it is for arithmetic circuits, for the synchronous communication model, where the corruption capacity of the adversary is threshold and the adversary is computationally unbounded, and the protocol, the BGW protocol was designed both for passive as well as malicious or active corruptions, and it considered static adversarial setting, but the security of the BGW protocol can also be proved against a more powerful adaptive adversary. Okay. So, the level of security which is provided or achieved by the BGW protocol is perfect security, often called as unconditional security or information theoretic security, and it is the first MPC protocol with these guarantees. So, the setup assumed in the protocol is that of private channel model. Namely, we assume that every pair of parties have a secure channel between them over which they can securely communicate. We can instantiate this private channel model by running a PSMT protocol if your underlying communication network is an incomplete graph. So, let us try to understand the arithmetic circuit abstraction first. So, as I said earlier, BGW protocol is a generic MPC protocol where the underlying function could be any function, and we assume that the function which is to be securely computed is a function over some finite field, okay, with some abstract plus and abstract dot operations. And we make several simplifying assumptions while presenting the BGW protocol. I stress that all these are simplifying assumptions and they hold without loss of generality. Okay, so, what are those assumptions? First, every party has a single input for the function. Okay. So, we assume that the function f small f which the parties want to securely compute is an n array function, namely it takes n inputs, one input is going to be provided by each party. So, the input of the ith party will be some field element xi, which will be a private input known only to the party pi, and the function is a single output function. So, the function output and the function is a single output function, and that function output is supposed to be learned by everyone. Okay. So, these are two simplifying assumptions. Of course, the protocol can be easily generalized for the case when every party has more than a single field element as input, and where the function can have different outputs for different parties. And the third simplifying assumption is that the function is a deterministic function. That means internally during the computation internally the function f computes its output as a deterministic function of its input. That means the output will remain the same if the inputs are same. Okay. So, as I said, these are some simplifying assumptions without loss of generality. So, even if every party has more than one input, or if there are several outputs of the function, say n outputs where the ith output is supposed to be known only by the ith party, or if the function is a randomized function, all those things can be easily handled by the BGW protocol. So, since the function f is an arbitrary function, we assume that the function f is represented by some publicly known arithmetic circuit over the field, okay, and that circuit will have some gates over the field. So, let us try to understand the various gates here. So, the first layer of gates in the circuit will be the input gates, namely the respective input values of the parties. Then in the circuit we can have some addition gates over the field. So, for instance, this is an addition gate here where the output of the gate is the addition of the inputs, where the addition is the underlying addition operation of the field. The circuit can also have some multiplication gates over the field. It can also have some gates where a multiplication is performed by some publicly known constant from the field, and then we have the output value. Okay. So, depending upon what exactly is the function small f which the parties want to securely compute, we have a corresponding arithmetic circuit representation for the function small f, and that arithmetic circuit will be publicly known because the description of the function f is publicly known. Okay. So, the function f is publicly known, that automatically implies that the circuit is also publicly known. Now, you might be wondering, is it possible to always represent any computable function small f as an arithmetic circuit over some finite field, and the answer is yes. This arithmetic circuit abstraction is without loss of generality. Why so? Well, it is a well known fact that if you take any function or algorithm or computation, so when I say the parties want to securely compute a function, it is as good as saying that the parties want to perform some computation or run some algorithm that is abstracted by a function. So, any algorithm or computation can be represented by a Boolean circuit, okay, consisting of some universal gates, say the NAND gates, and the NAND gate can be composed of and negation gates or NOT gates. Okay. So, that Boolean circuit can be easily simulated by an equivalent arithmetic circuit over the field. That means, whatever is the computation which is supposed to be carried out by that underlying Boolean circuit, corresponding to that Boolean circuit we can always find an arithmetic circuit which also performs the same computation. How we can do that? Well, we can say the following: we take a field and that field will have the additive identity element 0. So, the bit 0 in the Boolean circuit can be mapped to the additive identity 0 of the field. In the same way, the field will have a multiplicative identity element 1. So, the bit 1 in the Boolean circuit can be mapped to the identity element 1 of the field. And now, wherever in the Boolean circuit we have a negation gate that can be simulated by performing this operation over the field. That means, corresponding to every NOT gate, we can write down a gate over a field, namely a subtraction gate, and remember, over the field there is no subtraction. Subtraction is nothing but adding with the additive inverse. So, we can represent, or we can simulate the effect of NOT of B by an arithmetic gate over the field, a plus gate performing this operation, and wherever there is a Boolean AND gate involving the bits A and B in the Boolean circuit, that can be simulated by an arithmetic gate where we perform the multiplication of the mapped A and the mapped B, right. So, that means corresponding to every Boolean circuit B sir, I can write down an arithmetic circuit, okay, where the sizes of the size of the Boolean circuit and the arithmetic circuit will be almost the same. There won't be too much of blow up. That means, if the original Boolean circuit is an efficient side circuit, that means it represents an efficient computation, then the corresponding arithmetic circuit is also an efficient circuit representing an efficient or polynomial time computation over the field. Okay. So, that is why this arithmetic circuit abstraction is without loss of generality. There is I am not making any sophisticated assumption by making by assuming that the circuit is represented by some arithmetic circuit over a finite field. Okay. It turns out that computing the function small f over the inputs of the parties is equivalent to evaluating this arithmetic circuit over the inputs x1 to xn. Why so? This is because if the parties make their inputs x1 to xn public, okay, then anyone can compute the output of the function by evaluating each gate, namely if the values of x1, x2, x3, x4 is known publicly, and then since the circuit is publicly known, everyone can find out what will be I sub 1, everyone will be able to find out what is I sub 2, everyone will be able to find out what is I sub 3, and then everyone will be able to find out what is y, and y is the corresponding function output. So, this is called circuit evaluation in clear. Why circuit evaluation in clear? Because the entire computation is performed over clear values in the sense that all the values during the circuit evaluation right from the input to the intermediate values are known to everyone. Okay. So, for instance, if I take this example circuit which represents the computation x1 plus x2, and then you have product of x3 and x4, and then that is multiplied by 6. This is the function small f. Okay. Now, if the parties publicly declare their inputs to be 4, 3, 6 and 0, assuming that all the inputs are over the field Z7, Z7 means it has the elements 0 to 6, and all the addition operations are addition modulo 7, and all the multiplication operations are multiplication modulo 7, then anyone can find out what is the value of y. Okay. So, the value of I sub 1 will be 0 because 4 plus 3 over the fields Z7 will be 0, 6 into 0 will be 0, 0 into 0 is 0, and 0 into 6 is 0. So, 0 is the function output. Okay. So, this is called circuit evaluation in clear. So, what we understood here is that computing the value of the function is equivalent to evaluating the arithmetic circuit over the inputs of the parties. But definitely this process of circuit evaluation in clear violates the privacy requirement okay, because the input of all the parties are publicly known. Okay. The inputs of all the parties are publicly known, but MPC requires that the inputs of the parties should remain as private as possible. So, definitely this is not the way to perform secure multi-party computation. So, the BGW protocol performs the circuit evaluation in a different way, and the form of circuit evaluation done in the BGW protocol is called as the shared circuit evaluation. So, here is the idea of the shared circuit evaluation, assuming that the adversary is a passive adversary. And what is a passive adversary? By passive adversary, I mean that the corrupt parties who are under the adversary's control, they do not deviate from their protocol instructions. Whatever instructions they are supposed to follow as per the protocol, they follow that. They do not deviate from that. So, it is a weaker form of the adversary compared to the Byzantine or malicious adversaries. Of course, we want to design the BGW protocol for malicious adversaries, which we will design soon, but right now I am trying to explain you the idea used in the BGW protocol, assuming that we are in the passive corruption model. So, I am demonstrating the idea assuming we have 4 parties here, out of which T could be corrupt in a passive fashion, and where T is less than n over 2. You might be wondering why this number T less than n over 2. Again, in the first part of the course, we have proved that this condition is a necessary condition if you want to design a perfectly secure MPC protocol in the presence of T passive adversaries. Okay. So, that is why if you have n is equal to 4 parties, at most one of those 4 parties can be passively corrupt, then only the BGW protocol will provide you all the guarantees. If more than one party gets passively corrupt, then the protocol may not provide you the required security guarantees. So, the parties will not be knowing well in advance who will be the T corrupt parties. They only will have a bound on the number of corrupt parties, but they will not be knowing the exact identity of the T corrupt parties. So, for instance, it could be the first party who get corrupt or who get corrupted during the protocol execution, or it could be the second party, or it could be the third party, or it could be the fourth party. So, instead of performing the circuit evaluation in clear, the BGW protocol will perform shared circuit evaluation, and where each gate will be evaluated in a shared fashion. What does that mean? So, to begin with, the inputs of respective parties will be secret shared by the corresponding input owner. So, what does that mean? So, party 1 owns the input x1. It will act as a dealer and invoke an instance of n T out of n secret sharing scheme and secret share its input. So, it will give a share of x1 to second party, to the third party, to the fourth party, and one share it keeps with itself. So, let us call the shares of x1 as x11, x12, x13 and x14. These shares are computed by P1 because P1 is the owner of x1. So, it is now not giving the value of x1 to any single party, but rather it is giving a share of x1 to every party, and those shares are computed randomly by running an instance of T out of n secret sharing scheme. In the same way, the second party who owns the input x2, it computes 4 shares for its input x2 and 1 share it provides to each party. So, the first party will be provided a share x sub 2 1, the second party will be provided with a share x sub 2 2, the third party will be provided with a share x sub 2 3, and the fourth party will be provided a share x sub 2 4. Same is done for the input x3 and the same is done for the input x4. Now, let us stop here for a moment and try to understand how much information an adversary who can corrupt up to T parties learn about the inputs of the other honest parties. Okay. So, it turns out that adversary will learn at most T shares corresponding to the inputs of the honest parties, but those shares correspond to an instance of T out of n secret sharing scheme, and the privacy property of T out of n secret sharing scheme guarantees that even if up to T shares are given, leaked, compromised, adversary will not learn what exactly was the underlying secret. That means, for instance, if P1 gets corrupt, then of course P1 will know X1 because X1 is the input of P1. So, it will know its own input, but it will not be knowing X2, because for X2 it will only learn this share X sub 2 1, and the probability distribution of X sub 2 1 will be independent of the exact value of X2. So, adversary will not be able to tell what is X2, adversary similarly will not be able to tell what is X3, because corresponding to X3 adversary learns only a single share here, and in the same way adversary will not be able to tell what is X4, because corresponding to X4 the adversary learns only a single share. So, that means if the inputs are secret shared in this way by the respective input owners, then the inputs of the honest parties, by honest parties I mean the parties who are not under adversary's control, their inputs remain private, they are not leaked. Now, once the inputs for the function are secret shared, the parties next maintain the following BGW gate invariant for each gate in the circuit. They try to evaluate the gate in a secret shared fashion, where the gate invariant is the following. If the inputs of the gate are secret, if the inputs of the gate are secret shared in a T out of n secret shared fashion, then the parties then the protocol ensure that the parties have T out of n secret sharing of the gate output. That means, the inputs of the gate were not available in clear, and so is the output of the gate. For the inputs of the gate, each party had a single share, and even for the output of the gate, somehow each party will have a single share, such that the vector of shares for the inputs of the gate and for the output of the gate correspond to an instance of a T out of n secret sharing. So, what does that mean? So, the first gate in this circuit is this plus gate. If X1 and X2 would have been provided in clear, as it would have happened during circuit evaluation in clear, everyone would have learned what is the value of I sub 1, but now no single party knows the full value of X1 and X2. Okay. But everyone has a share for X1 and a share for X2. So, using the BGW protocol, a gate invariant will be maintained. How exactly that gate invariant is maintained? That is the crux of the BGW protocol, and that we will discuss later. But now what is going to happen is each party will perform some operations on its shares of X1 and X2, and that will ensure that each party gets a share of the intermediate value. So, that means collectively the vector of shares I sub 1 1, I sub 1 2, I sub 1 3 and I sub 1 4 correspond to a T out of n secret sharing of the exact intermediate value I sub 1. In the same way, the gate invariant will be maintained for the next gate, namely for this multiplication gate the parties will perform some operation on their respective shares for the inputs of this multiplication gate, and somehow the parties will get respectively their shares for the output of this multiplication gate, namely P1 will have I sub 2 1, P2 will now have I sub 2 2, P3 will have I sub 2 3 and P4 will have I sub 2 4, such that this vector I sub 2 1, I sub 2 2, I sub 2 3 and I sub 2 4 corresponds to T out of n secret sharing of the exact intermediate value I sub 2. And then they go to the next gate, and again following the BGW protocol they maintain the invariant for the next gate, and like that once all the gates are evaluated as per the BGW protocol in this secret shared fashion, each party will be now available with a share for the output of the function. Okay. So, P 1 will have a share y sub 1, P 2 will have a share y sub 2, P 3 will have a share y sub 3 and P 4 will have a share y sub 4. And once the shares for the output value are available, the parties exchange the shares, their respective shares for the output value by making those shares public. Okay. And once all the shares of the output value are made public, the parties can apply the reconstruction algorithm or the reconstruction function of the underlying secret sharing and learn the function output. Okay. So, now you might be wondering how exactly this gate invariant is maintained. Well, as I said earlier, that is the crux of the BGW protocol. Maintaining that invariant may require interaction among the parties depending upon what is the type of T out of n secret sharing is used and what is the type of the gate. Those details will be coming later. Now, intuitively this protocol maintains the privacy property even if T out of the n parties get corrupt, because throughout the interaction each value except the output value y remains secret shared in a T out of n secret shared fashion. Okay. So, that means for each value, namely x 1, x 2, x 3, x 4, I 1, I 2, I 3, right, all those values, each party will have only one share, and since adversary could corrupt up to T parties, adversary will have T shares for each of those values, and those T shares will not reveal the exact value of those values, the exact value of those x 1, x 2, x 3, x 4, I 1, I 2, I 3. Okay. So, that ensures that the privacy is maintained. This is not like your circuit evaluation in clear. And interestingly, the BGW protocol uses the T out of n Samir's secret sharing scheme, which we had seen earlier, due to its linearity property. So, we will see what is the linearity property. Due to this linearity property, while maintaining the gate invariant, the parties need not have to interact while evaluating the linear gates in the circuit. So, what is the linearity property? So, recall the Samir's secret sharing scheme is as follows. If you have a secret S over the field which needs to be secret shared, and if you have a publicly known setup, namely you have n field elements which are publicly known, which are distinct and non-zero, then to share a secret S, what the dealer can do is the following. It can pick a random T degree polynomial whose constant term is the secret to be secret shared, and the share for the ith party is the evaluation of the polynomial or the value of the polynomial at alpha I. Now, imagine there is another dealer who has secret shared a value S prime using an instance of Samir's secret sharing. For that, it has picked a random T degree polynomial. Let me call that polynomial as the B polynomial. The constant term of the B polynomial is S prime and all other coefficients are randomly chosen, and the shares for the secret S prime is generated by evaluating the B polynomial at alpha 1, alpha 2 and alpha n. So, imagine there is a publicly known value C from the field, and every party multiplies that value C with its share of S. That will give a vector of values, vector of n values, where the ith component of that vector will be available only with the ith party. Now, collectively if I view this vector of new values V 1, V 2, V I, V n, what it constitutes? It constitutes a T out of n secret sharing for the secret C times S. This is because if S 1, S 2, S I, S n constitutes a vector of Samir shares for the secret S, namely those values were lying on the polynomial A, then I can say that the values V 1, V 2, V I, V n lies on a T degree polynomial C times the A polynomial. So, the C times A polynomial will be a T degree polynomial, and this c times a polynomial, if I evaluate it at if I evaluate it at alpha I, this will give me the value V I. So, that means collectively the vector of new values V 1, V 2, V I, V n constitutes a T out of n secret sharing of C times S. That means, if a value S is already secret shared among the parties, and if there is a publicly known constant C from the field, then to generate a secret sharing, a T out of n secret sharing of the value C times S, the parties need not have to interact. They can just multiply locally their respective shares of S with this constant C, and that will give them their respective shares for the value C times S. So, that is what we mean by linearity operation here. In the same way, if the parties want to compute a secret sharing of C plus S, where C again is a constant from the field, then what the parties have to do? They do not have to interact with each other. Each party can just go and locally add the value C to its respective share of S. So, P I can add C to its respective share of S, namely S I, and that this operation will result in a vector of values. That vector of values will now lie on a polynomial whose degree is T and whose ith point is the ith component in this vector. And in the same way, if I want to generate, if the parties want to generate a T out of n Samir sharing of S plus S prime, where S and S prime are secret shared by instances of Samir secret sharing, then again the parties need not have to interact with each other. Each party just has to locally add its share of S and S prime. That will give the party its share of S plus S prime, because collectively now this vector W 1, W 2, W I, W n lies on a T degree polynomial whose constant term is the sum of the constant terms of the A and B polynomial. The constant term of the A polynomial was S, the constant term of the B polynomial was S prime. That is why the constant term of the A plus B polynomial will be S plus S prime, and this A plus B polynomial when evaluated at alpha I will give you S I plus S I prime, which is nothing but the ith component in this new vector. So, that is what we mean by the linearity of Samir secret sharing. So, the linearity property basically tells us that if you have inputs which are secret shared, and if you want to perform any linear function, a publicly known linear function of those secret shared inputs, then that linear function can be computed in a non-interactive fashion, in the sense that the parties can apply the same linear function on their respective shares of the inputs of the function and apply the same linear function on the shares of the input, that will give them the corresponding shares of the output of that function, output of the linear function. Okay. So, this linearity of the Samir secret sharing is a very powerful property which takes care of maintaining the BGW gate invariant for the linear gates in the BGW protocol. Of course, for the multiplication gates we have to do some more work, but we will come to that part later. So, with that I end this lecture. So, these are the references used for today's lecture. There are okay. With that I end this lecture. So, there are plenty of references available for the detailed description and analysis of the BGW protocol. My personal favorite is this first one, and as I said that we had the secure computation part 1 course where we discuss only the passive corruptions. So, whatever I have discussed in the today's lecture, you can find them in a more detailed fashion in the week 4 contents of the part 1 course, which is available at the following URL. Thank you.